So thank you very much. First of all, I would like to thank the organizers for their kind invitation here. It's always a pleasure to come to the Newton Institute and give a seminar. And so in this occasion, I'm gonna make a summary of results in the direction of minimization of interacting energies. And especially I will put an emphasis on the point in which I think there is more connection with the actual problem of free boundaries about the connection to obstacle problems. Okay, so we will see this later on. Okay, so what's the plan of the talk? First, I want to give you, well, the statement of the problem and the motivation why I came to this question. And so since it's right after lunch, we will have some fun at the beginning. And then I will go into details. And then I will explain you several things related to this problem that we were able to do in the last 2-3 years. And then I will concentrate in the main part of the talk, which is what can we say about minimizers for these repulsive attractive potentials. Okay? So let's start by the motivation and the statement of the problem. So it's a very, very simple question that you want, in principle. So I have a given potential that I'm going to call u of x. Now I'm going to assume that it's a nice function except maybe at the origin. So think if you want that it's a radial potential. And then I have m particles which are interacting through that potential. And I'm going to consider the interaction a first order model, in the sense it's not a second order Newton's-like equation, but rather like a first order in time system of ODEs. So you want, you can think about it a kind of relaxation limit from a second order model. So the velocity of each of the particles, is just computed by taking the total sum of the forces or the interactions of particles which are located at xj and to xi through these given potentials, so gradient of u. Okay, so in this way you have, let's say, the system of m particles. So the question is, obviously you can write associated to this system of m particles a continuous version. How the continuous version look like? So if you want to write what is the continuous velocity field as associated to the system of m particles, it's easy to guess that if you have a continuous density of particles located at time t located at position x, then the velocity field that you want to write is the continuous version of this is just the convolution of gradient u x minus y rho y. So any infinitesimal mass located at position y will produce a force gradient u of x minus y. So what you expect for a continuous PD model for this system of m particles is a continuity equation of that form. Okay, so you have a continuity equation that gives you the evolution of the density of particles, where the velocity field now is not linearly coupled to the density. Just you compute gradient of the potential come both with rho, with the minus sign, it's just a convention. Okay, so the question is, well, you have this non-linear, non-local equation. Now let's see what can we say about, let's say, the long time asymptotics. So just to summarize again, typically, so I have, I call the u the interaction potential. The minus gradient of u give me the attractive repulsive field. I will typically assume that the potential is repulsion in the short distances and attractive for large distances. This is just a typical case that happens in most of the applications, in fact. Although there are very good and interesting studies in the case of fully attractive potentials too, okay? But the question I want to concentrate today is for which interaction repulsive attractive potentials do we get convergence towards non-trivial steady states? And how can we find these stationary states, and what are their properties? Properties in terms of qualitative properties I can prove on those steady states. Obviously, that question is interesting from the not only from the point of view of the long time asymptotics of that PD I show you, but also in terms of variational calculus. So the first thing that you realize, in fact, about this PDE. So I come back to the continuity equation, or over here. So the first thing that you realize is that you have a natural Lyapunov functional in the system. This is something that we knew for a long time, since I started to work with Macan and Villani in this field of gradient flows of functions with respect to the Wasserstein distance. At this point, it doesn't really matter to know what it means, really, this sentence. But the important thing to realize is that you have a natural Lyapunov functional, which is the total potential energy. So you just compute the double integral ux minus y rho x rho y. Then, at least formally, the equation, you can write it in this way. So it's a continuity equation where the velocity field is, in fact, minus the gradient of the formal variation of f with respect to rho. So then it's quite easy to check that, at least formally, if everything is allowed here, that the derivative in time of the functional along a solution of the non-local PDE gives you this expression minus rho, the modulus of the gradient of the variation square. Okay, so you know that at least formally this is a Lyapunov functional, and those steady states that you are interested in, the ones that you will see as a stable steady state for this equation, you expect them to be at least local minimizers of that energy. Okay, so now we came out to the question. The question is, we want to find local minimizers of the total interaction energy. Okay, so the total interaction energy is this. And I want to find them in the set of probability measures. And this is not because I want to complicate my life, but it is because it's the natural set to find them. I have a conservation of mass, so I can always assume that the mass is just 1, so this is not the issue. And find them in the set of probability measures because in some cases, depending on the regularity of U, the minimizers might be quite rough in the sense that they are not functions, but rather just measures concentrated on certain sets. I will show you examples later. So, since we want to work in this framework, we want to minimize this functional in the set of probability measures, we have a difficulty which comes from the fact that what is the right topology that we had to use here to talk about closeness, or about measures that are being closed, okay? So to talk in a precise way about local minimizers. So we'll come back to this difficulty later on. So let me just mention at this point the motivation that this question of minimizing interacting energy functionals of this form is something that is recurrent in many, many different areas of applications of PDEs and mathematical physics. One probably of the most classical ones is in statistical mechanics and crystallization. This is something that it comes back to the 60s and 70s, in which they were studying thermodynamic limits of n-particle systems, but typically there, the potentials are very, very singular at the origin, like Lennard-Jones or things like this. So you cannot really talk about minimization of the set of probability measures, okay? So in fact, most of the cases I'm gonna treat, all the things I'm gonna say, they will be potential which are much less singular than those potential used in statistical mechanics. Then let me mention that this is also related to some particular stationary states that appear in drift diffusion like equations in semiconductors, in astrophysics, in chemotaxis. This is also, there were things done in this direction in the 80s and the 90s. Now, this appears also in economic applications. Many people in min-field games, they call these kind of things, minimizers for interaction energies of that form are called in that field Cournot-Nash equilibria. Okay, but we are talking about the same thing. And more recently, you get the relation also with fractional diffusion. I will come back later on in my talk about this particular point. And also, that was also something that I learned quite recently talking to some probabilists in France. In fact, this, for very particular potentials, is related to eigenvalue distributions of random matrices. So it's a kind of recurrent question in many, many fields. And how I came to this, in fact, I came to this because I was working on some collective behavior models in swarming. And I just want to mention a little bit that because it's the motivation that triggered my attention to this particular question. Okay, and particularly in the case in which the potential is not too singular at the origin. So, in fact, this when I was at UCLA, like 6 years ago, doing a sabbatical for 6 months, I started to know what the people in the group of Andrea Bertozzi were doing. And they were doing some models that they call individual-based models, which are just particle models, for describing the formation of large-scale patterns in mathematical biology. It's not too important to get into the detail of that. Just that there are some models in which what you want to include are basic mechanisms of interaction between the individuals, and some of the models are just based on mechanisms like an inner repulsion, essentially that the guys, they don't want to be too close to each other. So you have an inner repulsion area. And all the individuals, they want to be somehow nearby, so they are some kind of social. So there is some attraction to be not too far away. And then they include some other mechanisms like alignment. But in any case, the important thing that I want to make the emphasis here is just that they include this attraction, repulsion kind of interaction. They do it at the level of second-order models. I don't want to get into too much detail there, just to show you some movie about one of the simulation of a second-order model. It's not the first-order model I showed you at the beginning, okay? But just for you to see that with just these two mechanisms, sun inner repulsion and sun attraction at infinity, they were able to get some patterns that they call flock patterns, in which all particles rearrange into certain shape, and they just move translationally into some direction. Okay, so the interesting thing that they wanted to know is how to find that shape, or how you find the spatial shapes of the locations of the points. In fact, this is quite related again to the minimization of that interaction energy. And in fact, the spatial shape, the location of the points, is directly determined by the stable states of some interaction energies. In fact, this simulation is for a particular potential, which is called the Morse potential, that will show up later on in my talk. Okay, good. So I think it's enough for the motivation. I hope that now we are motivated to know what is known about the minimization of the interaction energy. Okay, so yeah, the next thing I'm gonna do, so let's discuss about some steady states or local minimizers. I say local between quotes because we don't know if they are local or global. And the first thing I'm gonna do is to show you some simulations again, now with the first order model, the model I started, okay? So what I am simulating is this ODE. Okay, with all the particles equal, okay? And I'm simulating that with different potentials. I will tell you in the next slide which kind of potentials I'm using. I just want to show you in these simulations how rich or how different things can be depending on the potential. Okay? So these first two simulations, you see in both cases you have this fast tendency that all the particles, which are, of course are randomly chosen at the beginning, they go to certain circle of certain radius very fast. But while in this simulation, the particles, they are not happy when they arrive to the circle. There is some instability, and then they start to aggregate on 2 points. Okay? While here, they are perfectly happy to be in this uniform distribution on the circle, and they just rearrange a little bit up to when they are happy, and then they stay there. Here, the only difference is, as I said, the potential. And in fact, as you will see, it's a very simple potential in which I'm just playing with one parameter. Here you have, again, this fast tendency to the circle, but now they are not happy again on the circle, but the instability is a bit different. There is this kind of shape instability. The circle becomes like a kind of triangular shape, and then again, now the particles distribute onto this case into three different pieces of curve. Okay? And finally, in this case, you have that essentially they arrange onto some two-dimensional set. So I will unveil the mystery about which potential I was using in the next slide. But before that, let me mention that you can play with many other potentials. And here you have another simulation with another potential. Doesn't really matter now which kind of potential is, but just to show you that you can get more complicated shapes, like this kind of, the particles they get distributed into not connected regions, and you end up with this kind of soccer ball. By the way, this soccer ball maybe is the soccer ball that the Brazilians will give to the Argentinians to train very soon. So let's see. Okay, anyhow, so you have all these kind of different behaviors. So what I was playing here is playing with a very simple potential. So I'm taking a repulsive attractive potential. The simplest you can think is a combination of two powers. So x to the a minus x to the b. I'm dividing by a and b in such a way that x to the a is always divided by a is attractive, and x to the b divided by b is always repulsive, regardless of the sign, okay, and regardless of the dimension. So in principle, in these simulations, I was taking a larger than b and b larger or equal than Newtonian, 2 minus d, okay? And what I was doing essentially is to fix a to a certain value and moving b. So if b is large, large means that the repulsion is very mild. So b larger than 2. Typically you see the concentration on 2 points. When you get b smaller, you go to b smaller than 2. At the beginning you see this concentration onto the circle in this particular case. And then when b gets smaller and smaller, even before b equals 1, you see that this circle is no longer, the uniform distribution of the circle is no longer the preferred state. I mean, local minimizer as you want, or global minimizer. And then it becomes a bit, there is a kind of thickening stability of the circle, so it becomes with a certain length. So you have this kind of annular region, and then you see that when you decrease b more and more, this annular region becomes larger and larger, and eventually when you arrive to Newtonian, very close to Newtonian, gives you almost a full ball, okay? So essentially, what you see in the simulation is that when b gets smaller and smaller, the support of the stable local minimizer gets larger and larger. You go from points to lines, and then to two-dimensional sets. With simulations, it's hard to say, but with many, many points anyhow, it seems that never you get another dimension rather than integer. You go directly 0, 1, 2, okay? And of course, if you go below b, that you can go, below b equals 0 in 2-dimensional, or in general, you go below 2 minus dimension, so you go below Newtonian, you can still arrive up to minus d, which will be the limit of local integrability. And in that range, you always see, of course, the full ball, okay? Okay, I will come back to that later on. Okay, so let's try to understand some of the things that we have seen in the simulations, and let's see what we are able to prove, really. So the first thing is that always, I want to convince you of something that we already saw in some of the simulations, obviously, is that always you have a particular stationary state. So just to see that there are a stationary state that sometimes are stable and sometimes they are not. So always the uniform distribution of certain circle is always a stationary state. And this is rather obvious to check, just because of symmetries. Just because of symmetries, you can just compute the balances of forces in any point on the boundary, And just because of that is uniform on the circle, you see that the components which are not in the radial direction, both for attraction and repulsion, they balance each other. So then it's, you have just an effective force in the attraction and effective force in the repulsion. And that's, you just look for the radius in which there is a perfect balance. So that's easy to check. And then one of the things that we did, that I'm not gonna give you details, is to check under which conditions the uniform distribution of the circle is stable or not. Some of the simulations that we saw here we saw a case in which for that range of parameters is stable, while here you have in both cases instabilities. In this case, they give you the instability leads you to points. In this case, it leads you to pieces of curve. In this case, it leads you to some two-dimensional set. So you can have several stationary states. You have non-uniqueness of stationary states. The thing is that you want to know which one is stable or not, which one is the local minimass or not, or global minimass or not of the energy. Another thing that we were able to show is some bounds on the dimensionality of the support. And let me explain this a bit more in detail, because this is more connected to what I want to concentrate later on. So I need now to introduce in which sense I talk about local minimizers, okay? So unfortunately, as I said, I'm working in the set of measures because it's the natural thing, okay? And I need to work, possibly I have concentration on points or on lines. So I need to talk precisely about local minimizers in some measure sense. So the kind of distance that we use is what is called the Wasserstein infinity distance. Unfortunately, it's a bit more complicated to work than other transport distances that you are more probably accustomed to it, like the Wasserstein 2. But the idea is very simple. Instead of computing the L2 cost, so what you are computing is the maximal possible displacement when you transport one measure onto another. And out of this maximal displacement, you take the best possible one. So you take the infimum. So imagine that a measure is a kind of piles of euro coins, but no, pounds, 1 pound coins, okay? And then the other measure is another pile of coins, and you want to transport this one onto this one, so you want to transport all the coins from one side to the other, putting in the same location. Because what you are computing is from each way of sending all the coins from this measure to this measure, I compute the maximal displacement I do between 2 coins. And then from all the possibilities of doing this, I take the best. Okay, so that's Wasserstein infinity. Why this is more advantageous to me to do things theoretically is because it's a good topology if you want to think about linearization of steady states of a dynamical system. Okay? Associated to that, you can always define what is called the empirical measure, which is the sum of the Diracs located at the points xi of t. So you would like to somehow have a good control when you linearize around that measure. And then, obviously, when you will linearize around an equilibrium for the set of ODEs, we use Taylor's theorem. So perturbation is that you send the particles very close by. So this is precisely why I need W infinity, because it tells me that I cannot send the particles very far. Okay? So if I send the mass to points which are nearby the point, this is a small perturbation in W infinity. But if I send epsilon mass from this location to the moon, it's very large in W infinity, but not in W2. So that's why W2 is a bit worse for me. Okay? Anyhow, there is a pragmatic point here, why to work in W infinity, because it's the Corsair topology. So whatever I say for W infinity, it will imply anything for the other notions. So what I mean is that a local minimizer of the functional in W2 is also a local minimizer in W infinity, but not vice versa. So anyhow, it's a good place to start. Okay, so now let's be rigorous. Okay, so I start stating the first assumption on the potential. So I'm going to assume that the potential is bounded from below, lower semi-continuous, and L1 log. Okay, so I already are, for the case of powers, I'm already assuming that the repulsion cannot be stronger than dimension. Okay, minus dimension. Good. So the first thing that you can do, and it took us a while, is to find a suitable way of writing Euler-Lagrange conditions in W infinity. So let me explain you then this result, which is the starting point to connect it to, Okay, no, I mean, I will come back immediately there. So what happened? Okay. Very good. Now I understand how it works. So this result, what it says is the following. Assume that mu is a local minimizer in W infinity of the interaction energy. Okay? Remember that the interaction energy is f of mu double integral of ux minus y d mu x d mu y. Okay? So then what I do is you define the potential generated by the local mean, which is u combined with mu. Okay? U is the potential there. So you define the potential associated to that. So then the Euler-Lagrange conditions in W infinity, what they say is that the potential, you take any point in the support, x naught, so that's the support of mu. Okay, let's assume that this compound is supported. I think it's in the assumptions too. If not, then let's do it. No, it's there. Locally compactly supported. Okay, so I take any point in the support. What it tells you, the Euler-Lagrange condition, is that this point is a local minimizer in the standard sense for the potential. So psi of x is larger or equal than psi of x naught for almost everywhere in a ball of center x naught and radius epsilon. And epsilon is the epsilon of the ball in which mu is a local minimizer in W infinity. So the epsilon is just given by this condition. It's important to know that the epsilon doesn't depend on x. So essentially, it's telling you, I mean, if the measure would be nice, if the support of the measure would be like what I did, it's telling you essentially that potential is constant in each connected component, maybe different constants. Okay, this is what it's essentially telling you. It's a bit more technical because it's almost everywhere, and you have to be careful with this because it's almost everywhere with respect to, in fact, I mean, it's almost everywhere Lebesgue measure. Okay? As I said, the epsilon is uniform. Now let's see just a comment to compare the Euler-Lagrange conditions to Euler-Lagrange condition in a better, with a, let's say, stronger topology. If you do it in W2, in fact, the Euler-Lagrange conditions are a bit better. You even know exactly what I just said. The potential will be constant, mu almost everywhere, in the support. It's constant mu almost everywhere, equals to that value, 2I is the energy. And in fact, the potential, you can prove, is larger or equal than the same constant in general outside that almost everywhere. So now you start to see the connection with the obstacle problem, if you are accustomed to the obstacle problem. Anyhow, I'll come back to this in a point, in a moment, in a couple of slides. So, what can we do just based on these Euler-Lagrange conditions? So I will come back to the point of regularity, which is the main point of my talk. So we can estimate, as I said before, the dimension of the support. This is the first thing that we did. And these are also simulations just to convince you that this is not a 2D thing. I mean, we did simulations in 3D. And again, if you fix the A to some value and then you start playing with the B, if B is larger than 2, using concentration on points. If B is below 2 and larger than 1, you see that now it concentrates on 2 surfaces. Then if B gets smaller, then it concentrates on 2 larger surfaces. I mean, they get connected and so on. If you get B below 0, then it becomes a 3D ball. Even if you don't see it, we check it, but it's a kind of 3D ball. Okay, so in fact, what we were able to prove rigorously are the following facts. The first one is related to the case of mildly repulsive potentials. So what I mean is when the potential is not too repulsive at 0, in that case, when B is larger than 2, then, so essentially the assumptions are always that the potential behaves like the corresponding power at the origin. It hasn't got to be a power though. But with B larger than 2, then what we were able to show is that any local minimizer in W infinity cannot have any smooth component in its support of dimension different from 0. Okay? So what we were able to show is that in the support of a local mean, there are no curves, no surfaces, no set of dimension d. The only possibility of this integer is 0. We were not able to show that is not a set of Hausdorff of non-integer Hausdorff dimension, but this is what we see numerically. In fact, we are working on that. The conjecture in that case is that it's just a 0-dimensional set and maybe just a finite number of points, but we don't know how to prove this. If B is less than 2 and larger than Newtonian, so when B gets smaller and smaller, when the repulsion gets stronger and stronger, again, if you have a local minimizer of the energy with respect to W infinity, so, and the potential behaves like a power in that range, then what we were able to prove is a bound from below on the Hausdorff dimension of connected components of the support. So the Hausdorff dimension of any connected component in the support, let me call it S, is larger than 2 minus B. So let's first understand the result. So this is telling me that when B gets smaller and smaller, the dimension of the support is getting larger and larger. Okay? And then we see also the point that when B arrives to Newtonian, which is 2 minus dimension, by the way, this should be larger or equal, then you get to full dimension. Okay? So, of course, this doesn't prove yet what we see in the simulation that looks like is quantized. So you go from 0 to 1 to 2, or in 3 dimensions, 0 to 1 to 2 to 3. But, I mean, at least we have this good bound from below. So from where it comes, this result? So let me just give you, this is not on the slides, let me just give you an idea because I think it's good to make this connection today with the audience I have. So the strategy is purely variational. You assume it's not true, then you construct a better competitor. But what you use to construct a better competitor is that the fact that the potential has a local mean, you can write a kind of differential version of it. You can prove, in fact, that the Laplacian of psi at points on the support, and this Laplacian I'm going to put it at tilde because the potential, I mean, I have to give a sense to that. So there is a kind of Laplacian of the potential that I can prove that, in fact, it has a sign on the support of the local mean. And if you play with that inequality, that inequality tells you that the double integral of x minus y, b minus 2, d mu x, d mu y is finite. After all the long work that you do, this is what you get. Okay, this is what you prove. That for the measure mu, for the local mean, you have that this double integral is finite. So people that have worked in capacity recognize that this is telling you that the capacity of the measure mu with certain exponent is finite. And there is a famous result in geometric measure theory that tells you that if the capacity is finite, then this implies exactly my result. This implies that S is larger than 2 minus 3. Okay, so I was using just geometric measure theory at this point. This is what is called Frossman's lemma. Okay? Of course, to arrive to this, we just, as I said, what we use is to, we proceed by contradiction. We assume that it's not true. We build a better competitor. We prove that for that better competitor, we have this inequality. And from this inequality, we work a bit to get to this. I mean, that was the objective from the very beginning because we knew that this will imply some bound on the dimension. Okay? So this is the farthest that we got in that range to get advantage of these Euler-Lagrange conditions. To get, I mean, there are other results in geometric measure theory, and we are trying for a while to see if they can be useful for us, but still we don't see how to use them. Okay? So we don't know how to prove this quantization yet, for instance. Okay, so with this, I think I tell you everything about the case up to Newton. Okay? Now, let's continue getting advantage of these Euler-Lagrange conditions here in another direction. But there are two directions I want to show you. The first one, probably not that related to the title of my talk, but I think it's important, is in the direction of minimizers of the interaction energy. Probably now you got a bit anxious with me. Why? Because I never told you that there are global minimizers of the functional. I just talk about local minimizers. But do I have a global minimizer? Do I know how to prove that there is a global minimizer? So in fact, we didn't know how to prove that there was a global minimizer when we did that part of the qualitative properties. I want to convince you that it wasn't it wasn't that easy to get global minimizers. And in fact, it's a question that has been open for a while. And I'm going to explain you that we recently solved it in collaboration with Jose Alfredo Cañizo, who is here, and Francesco Patacchini, okay, who is also here. So let me explain you how we got first conditions under which you have global minimizers. Okay, so the first thing I'm already telling you here, the additional condition I need, apart from the previous one of bounded from below and local integrability, which are basic assumptions just to define the potential to have a bound from below, in order that we can prove the system of global minimizers. So let's try to understand this. This is usually called non-H stable. But let me first explain you what it means, and then I will connect to why it's called non-H stable. So I'm going to try to write in mathematical terms a very easy thing to write, which is that the energy at infinity costs more than near the origin. So what do I mean by that? What I'm going to assume is that the potential at infinity is larger or equal than some value. What best value than 0? Let's fix 0 as the value. The 0 here doesn't play any role. So let's say that the potential at infinity is larger or equal than 0. And then, on the other hand, let's assume that there is a measure for which the value of the potential energy is negative. So this means that at least for one particular measure, it's much better to be near the origin than be at infinity. Okay? This is in fact a condition that is known it was known in the statistical mechanics literature of the 60s and 70s as non-H stability. The people that were working in crystallization, that were working in how you, when you increase the number of points, how you get a crystal that fills the whole space, were working with precisely the opposite assumption, which is called H stable. That's why we call it non-H stable, because it's exactly the complementary case. Okay? So the result that we got says the following. If we have the potential under the assumptions, the basic assumptions H1 and this non-H stability, and we need a little bit more, that outside a big ball, the potential is increasing, say. There are plenty of other assumptions that are equivalent to that one that we can use, but this one is one of the simplest. So say that the potential is increasing outside a large ball, then we can prove that there exists a global minimizer for the energy, and moreover, it's completely supported. Okay? So how we prove this? Well, by the way, this is what I just said, that this is our work in collaboration with Cañizo and Patacchini. And let me mention also that there is a very recent work of Simeones, Lepches, and Topaloglu that they were able to prove the systems part, but not the compact supported part, using Lyon's concentration compartness principle. So how we prove this is by proving that at each point in the support of this measure of a global minimizer, and we use for that the Euler-Lagrange conditions, we prove that there has to be at least a minimal amount of mass, okay? Jose Alfredo had this very good idea to how to estimate uniformly the small amount of mass that you have at each point of the support. And with that, using the Euler-Lagrange conditions and many other ingredients, one is able to get that kind of result. But I don't want to get into many details here. Just to say that that is also a very interesting issue, and that we have solved it in part recently. So we know that, and just using again the Euler-Lagrange conditions, we have global minimizers which are completely supported. Let me also mention that, well, this applies, well, I don't want to show this. This applies to these particular cases. So this applies to power laws in all the range, A larger than B larger than minus dimension. This applies to the Morse potential, and for the Morse potential is quite interesting. The Morse potential, now you see it for the first time. That's the one that was simulating in that simulation I showed you for the second order model. It's a combination of exponentially decreasing function of the radius. So for that potential, it depends on the constants there, and depends on the ratio between CA, CR, LA, and LR. You may have that is H stable or not. And in fact, it's very nice because it coincided exactly with some of the descriptive numerical simulations that the group of Andrea Bertozzi at UCLA did for the other model. So in fact, we get the system of a global minimizer exactly in the range that by the numerical simulation you were expecting to have it. So let me also mention one thing. We said I wrote that we get compactly supported for global minimizers. In fact, you can also prove in some cases, for instance, in the case of powers, when A is positive, then the limit of the U at infinity is plus infinity. You can really prove that even local minimizers in W infinity are also compactly supported. Okay? So assuming compact support for a local mean in W infinity, in fact, at the end of the day, it wasn't that of a strict assumption. So everything I said before for compactly supported local minimizers in W infinity are things that you can apply in this case when A, for instance, is positive. Okay, and now in the rest of the talk, I'm going to concentrate on the relation with obstacle problems. So how much time do I have left?
About 10 minutes.
Okay, good. So let me talk about now about the title of my talk, Regularity of the Local Mean. So let me start by saying that this part on regularity of local minimizers, this is a very recent work with Matias Delgadino, an Argentinian student of Antoine Mellet in Maryland, that is not even still preprint. We are finishing now. It's work in preparation, but almost finished. And the result goes in the following direction. I'm going to first do it in the case in which the repulsion is just Newtonian. Let's start with that. We understand in that case, and then I explain you the general result. So now I'm going to work. So I think now is a good idea to do the following. So let's try. I know that I explained you many things, and probably you have lost track of how many things I told you in the previous slides. But I think if we do it for power laws, we can do graphically the summary very easily. So let's say that we are working with power laws now. Okay, just to have in mind some particular case. Okay. So, okay, let's say this is A, this is B. Let's say that this is 2 minus dimension. Let's say that this is minus dimension. Okay, so in the first part, I was talking to you about the cases in which B is larger than 2 minus dimension. So over here you have the case of points. Then when you get down, in 2 dimensions you will see the lines, and then in 2 dimensions you don't have too much space. This will be 1, no? And then this is 0. So then you will see the annular region over here. Okay. So now I'm going to talk to you about this case. The case say that the repulsion at 0 is like exactly Newtonian with any kind of attraction. And then I will discuss also cases below. Okay? So let's start with this case. Yeah, so what did I do with the
It's behind the computer.
behind the computer? Very good, thanks. So let's start by making precise the assumptions. So I'm assuming the basic assumptions that U is locally interval bounded from below, lower semi-continuous. And to say that the repulsive part is exactly Newtonian, what I'm going to say is that U minus the Newtonian is a good potential. Okay? So I'm going to say that U minus the Newtonian, I'm going to call it UA. That, if you want to think about it, the attractive part. But it could be also partially repulsive, but not too bad. The assumptions I'm going to do on UA is just that the Laplacian of UA is a nice function. It's an LP function with P larger than dimension. Okay? So what we are able to show is that you have a potential under those assumptions, then, in fact, any compactly supported local mean of the energy is bounded uniformly. So all the local minimizers are not only that the support is full measure, but in fact, the measure is just density, and the density is in L infinity. Okay? How we do this? Well, this is what I said in words before. And how we did this is to really make use now of the connection, deeply of the connection to obstacle problems. Let me show you that in the next slide. Also, just to announce, but I will do a bit more detail if I have time, the same thing, you can do it for more singular than Newtonian in the range minus d to minus d. So very similar assumption. You assume that U minus the fundamental solution of the corresponding fractional Laplacian in this range is a function which is LP with P related to dimension and the corresponding S here. But I have time, I'll do it. I write it. Okay, so how we did this? So the first thing is that once you are with the repulsion Newtonian, we were able to show some property about the potential that we didn't know before, which is at least that it's continuous. Okay? So the first thing is that under this new assumption, we know that the potential generated by the local mean in W infinity is a continuous function in Rn. And for those that know very well obstacle problem, this is somehow one of the basic things that you need in order to reproduce Evans' proof of the existence for the obstacle problem. This is exactly the strategy we did, and we use a kind of mean value kind of argument to get from that the continuity of the potential. And in fact, what we are able to show is that, and from where we really prove that it's an L infinity function, the local mean, is that the potential generated by mu is, we can characterize it as the unique solution of the following obstacle problem. So let's understand this, because this is the main point. So remember the Euler-Lagrange conditions. The Euler-Lagrange conditions are psi, which is U comboth mu, has to be larger or equal than certain constant, and here I'm calling C0, outside the support. And psi is equal to that constant on the support. And in fact, we know the value of the constant, but this is not important now. In any case, now I say really this because we know that psi is continuous. So I don't care about almost everywhere anymore, and this is important. So from here you get the first condition there. Now you use that U is UA plus B, that was our assumption. Yeah, plus B, yes, I think so. I wrote it like that. So then, obviously, if I take the Laplacian of psi, since if I take the Laplacian of psi, I will get This is formally the Laplacian of UA convolved with mu plus mu. Okay? Because the Laplacian of the Newtonian potential will give you the Dirac, so I get the mu here. So from here, you see that then you will get the inequality, because mu is larger or equal than 0, you will get the inequality that minus Laplacian is larger or equal than minus f, with f given by Laplacian of UA convolved with mu. Okay? So from there you have that inequality. The equality is obvious because then is when you are outside the support of mu. And the value at the boundary is just the value that we fix. Anyhow. And the way of reconstructing mu, if you have a unique solution of the obstacle problem, is that mu is, well, is obtained from the difference between f and minus Laplacian, as is the usual case in the typical obstacle problem. Okay? So the cornerstone of all the result was to prove that, in fact, when psi is continuous, then our problem, written in this way, is totally equivalent to that implicit obstacle problem. And I say implicit because the f is here, f is minus Laplace UA, Laplace UA, convolved with mu, then depends on the solution itself. So you see, it's not the standard obstacle problem. So let me comment on this. So, results that were done. So in fact, here we have two, no? So let's write this line. This point. This point is the case in which A is equals to 2 and B is equals to Newtonian. Okay, that particular case has been studied by many people. Particularly Caffarelli and Freeman did it already for semiconductors. So you just take A equals to 2, it's very special. Why? Because when A is equals to 2, UA is just modulus of x squared over 2. So you read what you get there. What you get there for f is that f is just a constant. It doesn't depend anymore on mu. And it's exactly the classical obstacle problem. So this point is a very particular case in which everything was known. I said Caffarelli and Freeman because they did it from the point of view of obstacle problem, but there are many other people that look at it from different perspectives. And anyhow, there we know that the solution is the characteristic of the ball. Okay? So there it was known that the solution is the characteristic of the ball, center 0 and certain radius in such a way that this has area 1. And that's the minimizer in that case. Okay? Other cases that are known. All this line. All this line. This corresponds to A equals to 2 and B between minus dimension and 2 minus dimension. And this corresponds exactly to the kind of fractional version of the porous medium equation that Caffarelli and Vázquez did some years ago. And that they study the Self-similar solution, they write the equation in self-similar variables, they study the stationary states. The stationary states coincide exactly in that case. Again, that is very particular because, again, the UA is x squared over 2. So what you will have in that case is a very similar obstacle problem to the one that is written there, but instead of Laplacian, you have some fractional Laplacian. Okay?
And the problem is not implicit, you can solve it.
Yeah, and the problem again is not implicit for the same reason as here, because the x squared over 2, this gives you a constant, and again, you of course, you took advantage of that, and then you can really prove the existence of the solution. Okay? So what I'm telling you about is about the rest of the cases. So when the attraction is anything, well, here it will be a power, but just with those assumptions, at least is equivalent to that. And what we were able to say is to take advantage of the regularity theory for the obstacle problem. So I cannot say, I mean, it's more difficult to get advantage of it because it's implicit, because of this. But I know that if Laplacian of U is good, even if mu is a measure, this guy is good. So then you take advantage of the regularity theory of the obstacle problem. Caffarelli did a lot of this in the case of the Laplacian In the case of the fractional Laplacian, it was also Caffarelli and Silvestre, or Silvestre alone, I don't remember. Silvestre alone, maybe. And anyhow, you take advantage of the regularity theory in both cases to say that if this is good enough, then you get information on psi. Okay? And from there is where you get the results. So I don't have too much time to tell you more on this, but let me just summarize then the result here. Here I am telling you, at least in the case of the Newtonian, so in this case, what we are able to show is that the minimizer is in fact a density which is not infinity, and you cannot expect better than this, because you know for this point, it's exactly a characteristic of a ball. Okay?
Let me ask you a question that
Yes.
could be important for the topic. In the case we solved, the solution had compact support.
Yes.
We solved now, in the cases that you are saying, can you?
I know that it's compact support because of the previous result that I mentioned with Patachini and
So
Jose Alfredo, but yes, we know.
Still, yeah.
We know. Let me be precise on this. Okay, we know that when A is positive, it's compactly supported. When A is positive, in the case of power laws.
Okay.
If it's not a
Because
power
of the
law,
attraction
if
at
the
infinity.
potential at infinity is plus infinity,
Okay.
I know that it's compactly supported. Okay.
So the next question is,
Yes.
do you have radial symmetry?
Yes, very good. Thank you for that question, because I planned to have said something about this before and I forgot. So just look at the interaction energy. So f of rho, 1/2 double integral of u, x minus y, d mu x, d mu y. So you cannot apply a typical trick of a Schwarz symmetrization, because it works for the repulsive but not for the attractive. So we don't know. And in fact, we know that in some cases it's not radial. We saw that there is when I am above 2 minus d,
Yeah.
numerically it's clear that there is a break of symmetry.
But numerics below? there is
Below
symmetry.
say that it's symmetric. We don't know how to prove that it's symmetric, okay, except in that line
Yeah.
that you take advantage of the fact that it's explicit.
Because the solution is unique.
Okay? So, in fact, as I said, what we know is that in that line is L infinity. Related to the radial symmetry, also uniqueness. What do we know about uniqueness? We only know that it's unique, again, in that line because you did it. And it's because the explicit case. We don't know uniqueness outside that. Okay? So in that line, we know this is an infinity. In fact, Yang Hong Huan, that is a postdoc of mine at Imperial, before coming to Imperial, he was doing some works with Fetekau and Kolokolnikov. They were studying the radial case, just directly to check what happens with the radial. And for radial functions, they can prove that it's unique. And they proved that in this case, it looks like that, and here it looks like that. So the effect of the attraction is that when you are A is larger than 2, then instead of being the characteristic of the ball, it becomes concave. Below it becomes convex. It's compactly supported, and it has a shape like that. In the other case, in the case in which the B is below a Newtonian, here, in this range, what we are able to show, using again the regularity theorems for the fractional Laplacian, is that the density is even better. It's not only L infinity, but in fact it is in some C0 something. So there is not a jump on the boundary, like in this case, but rather you go to 0 with some alpha that depends on the S and the dimension. Okay, so this is what you get. But again, we don't know uniqueness in all the other cases here. Okay, so I think more or less I can leave it right now there. Just probably just to say the conclusion is written there. So what I show you is on one hand that the dimensionality of the support depends on the strength of the repulsion. When the repulsion is not, when you are above Newtonian, then I show you that company supported global minimass exist under very reasonable assumptions, and that if the strength of the repulsion is below Newtonian or Newtonian, then immediately your minimass is very good, in fact, L infinity or at least continuous. And yeah, that's all. Thank you.
More questions or comments?
So what is, according to you, the main open problem from the point of view of...
Well, there are plenty.
Many of these problems are impossible still, right?
Well, some of them maybe. Yeah, so the thing is, above Newtonian, we see always in this region, say between, at least for sure into the, say in the region between 2 minus dimension and 3 minus dimension, between 0 and 1 in 2 dimensions, you always see that numerically it seems that the solution is also, completely supported and nice in its support. But you see some, it's not so clear what happens at the boundaries, in fact, of these annular regions. So we don't know if there is really some concentration. You see concentration of points there, but it's very hard to say, to guess if there will be something that has a singularity at the boundary or not. So one of the open questions will be, for instance, if you are in this line with A equals to 2, and you are very close to Newtonian from this side, what happens with the local minimass in terms of regularity? So that, I think, is the first open problem that might be, we have some idea. So in general, close to Newtonian from above, I think that is one of the interesting questions, for instance. And from the point of view of larger than 2 minus dimension, to prove this kind of quantization, there are results in geometric measure theory that tells you that depending on the capacity of the measure, and if you have something better on the measure, you can say that the measure has to have, the support has to have integer dimension. There are results like this, but we don't know how to prove how to verify the hypothesis for the local minimassers. So we're stuck there.
Anything else? If not, let's thank the speaker again.